ask them to email me back as soon as possible. So,
yeah.
Did you guys hear me? So make sure you email me if you have not received my introduction to the mentors. Okay? And I'll try to solve the problem. So yeah, just shoot me an email saying that you haven't talked to the mentors, or you haven't received my email. That's fine, and I'll try to track everybody down. Okay, so today we have a lecture on spectrum splitting. Let's see, where is it? Okay, here. So happy Halloween. So we have lecture on spectrum splitting. Next week, remember next Thursday, November 7th, we have assignment 3. So make sure you work on that. And that's probably the most detailed assignment, technical assignment of the class. So I expect something substantial from all the teams. So make sure you spend some effort on this. The instructions are, of course, yeah, we went through these instructions several times, so I'm not going to go through it again unless someone has any questions. Okay. Of course, if you have questions, you can ask now or just email me. Okay. So let's jump right in. So today's lecture is on this idea of spectrum splitting to increase the performance of photovoltaics. So let's try to understand what the motivation for this is and what does spectrum splitting really mean. Okay, and I'll focus on a specific technology that was developed in my lab called broadband diffractive optics. So this is something we're very familiar with, both Apratim and I, and I'll kind of emphasize this aspect of it and why we think it's important. So first of all, the idea is we need to, the main impediment to widespread adoption of photovoltaics is cost. So, the reason why, any person doesn't put solar panels on their roof is because you have to put in, several thousands of dollars in order to put a substantial system, or let's say a useful system. And that's a pretty big barrier. So the question is, okay, can we try to understand where those costs come from? So there's been lots and lots of studies on this over the years, and some of the numbers are a little bit older, but I'll try to emphasize the key points. But we can look at how PV costs break down in a very high level perspective along 3 segments. So there's the module itself, which of course includes the panel, all the materials that go into the panel, including the silicon, the contacts, the glass cover, any aluminum frame, whatever, right? Then and that's little more than 50% of the total cost. The installation is a little bit less than 50% of the cost, but pretty substantial as well. So it's not the module cost itself, but of course installation, because you have to have electrician and you have to construction and so on. Then there's something referred to as this installation includes something called BO. So it's BOS/installation. So BOS stands for balance of systems, which includes things other than installation, things like transportation costs, regulatory costs, licensing, taxes, whatever, all the other stuff. So that's a pretty substantial portion as well. And the remaining cost comes from power electronics, which is also fairly substantial, but it's much smaller than the others. Now, the question really comes, okay, what can we do about this? Of course, for the module, it's pretty straightforward. We try to bring the cost down. For installation and balance of systems, the answer is not so straightforward, because how do you decrease these costs? Of course, you can try to make the panels lighter so you can transport them cheaper. But there are other approaches as well, which we will talk about today. Power electronics, there's not too much we can do other than, of course, as the technology becomes mature, you end up reducing the cost as well. Now, we are going to focus primarily on this balance of systems cost, because this is the part where a huge reduction could be achieved, particularly by increasing the efficiency. So that's where we'll focus on. And this has been studied in quite detail. This is numbers from about 9 years ago now, but the concept is still valid. This is a study done at George Washington University by Ken Zwiebel, which plots the cost of power, dollars per watt in DC power, as a function of the module efficiency. So this is not the cell, but the whole module, and goes from roughly 5% to, let's say, 40% or so. So those are representative numbers. And there are several curves here, and each curve represents a slightly different installation. Excuse me. First of all, each curve represents a different installation, like residential is the most expensive, commercial, tilted, commercial, flat. Tilted simply means it's pointing towards the sun. Flat means it's on a roof, like the roof of a warehouse or whatever. So it may not be tilted. And there's a few other things like tracking, one-axis tracking, two-axis concentration, two-axis high concentration, and so on. And of course, the cheapest one, all of this is non-tracking ground, which I'm not entirely sure why, but probably because of the tracking costs. But what's important to insight to extract from this plot, first of all, is as the efficiency increases, this cost decreases. Now, of course, this cost includes everything, all of the three segments that we talked about in the previous slide. But what you can see is that as efficiency increases, all of them decrease. This makes sense, because if you have a more efficient module, you only have to install fewer modules to get the same power output, right? So your installation cost goes down, obviously, and you only have to transport fewer modules, so your transportation cost goes down, all the good stuff. But what's really remarkable is actually what's pointed out at the bottom of the slide. If you take a 5% module, which let's say you give it away for free, it would have the same system price, $3.50 per watt for a residential rooftop, as a 15% efficient module costing about $1.50 per watt. So what that means is that the efficiency can have a huge impact on the price of power generated. So it's a very, very important factor. Another way to look at this data is in a slightly different fashion, is what's called the levelized cost of electricity, which is the horizontal axis here. This is, if you look at your utility bill, this is what you'll pay. It's measured in cents per kilowatt hour. A kilowatt hour is, of course, energy, whereas kilowatts is power. So this is plotting the module cost, which is dollars per meter squared in area, as a function of electricity cost in cents per kilowatt hour. Okay, electricity in the form of energy in the form of electricity. And of course, you will see these are logarithmic plot scales. So you see these straight lines, but as you increase the efficiency, you see the slope of the straight line increases. Okay, in other words, a higher, a more efficient module, as you change the module cost, the change of cost of electricity is less. In other words, you're less sensitive to changes in module cost. So if you're a module manufacturer, one other way to look at it is that you can actually charge a premium for your more efficient module, because the change in the output electricity cost is small. Okay, so from a manufacturer's point of view, also it makes a lot of sense. Now then the question is, okay, now we need to understand, okay, what limits efficiency? So the most fundamental reason for efficiency being limited is because of the fact that sunlight has a broad range of wavelengths. So this is the M1.5 spectrum, where this is plotting relative spectral output as a function of wavelength, and we know there's energy from UV, 300 nanometers, visible all the way into the infrared, and even longer. Now, this is cut off here because most silicon cells will stop absorbing after here, 1100 nanometers or so, because that's the band gap of silicon. And what's interesting is that it's extremely broad, right? This the wavelength goes from 300 to 1100 nanometers, which means the energy of the photon is very much changing as well. So a single bandgap material like silicon does not match the solar spectrum appropriately. And we'll see what that means shortly, but you can see from this plot and these percentages here that the energy is distributed. So in other words, there's 16% in the near infrared, 12.5% between 800 and 900, 15% 700, 800. This is the total percentage of the total energy. So if you can only collect this much of the light coming in, you've already lost a drastic percentage of the light that could have been collected. So this is a big potential loss. So let's try to understand the physics of why this happens. So this is a very much of a cartoon perspective, and you'll have another lecture on the physics of solar cells in a couple of weeks. So this will go into a little more detail. But from a cartoon perspective, a solar cell can be thought of as a PN junction, which has a band gap. So a semiconductor has something called a valence band, which is filled with electrons. Okay, and at a higher energy level, which is shown here, it has a conduction band. This is the bottom of the conduction band, which is filled with absence of electrons, which is also called a hole. So it's represented by these clear circles. And the valence band and the conduction band are separated by what's called the band gap, represented as Eg. Now, when a photon comes in to the material, the incident photon has some energy h nu, which we know, as we have talked about. The nu is the frequency, which is c over lambda, lambda being the wavelength. So longer the wavelength, lesser the energy. Now the photon comes in, several things can happen. One, let's say the energy of the photon is equal to the band gap, h nu equals to Eg, then the photon may be absorbed by the material, which means that it might kick out an electron from the valence band, and that electron has sufficient energy to go up to the conduction band. And this is called absorption. And this is good because now you have an electron in the conduction band, which can move around and go to the terminal. You have a hole in the valence band, which can move around and go to the other end of the terminal and form a current. Okay, so this is what you're looking for in a good solar cell. But there are other things that can happen as well. If your energy of your photon is less than the band gap, then something called non-absorption loss happens. The photon does not have energy to kick the electron up, it just passes straight through. Okay, so the energy of the photon is less than the band gap, it's not absorbed, it just passes through. And this is a situation for photons whose wavelengths are longer than the infrared. Okay, because those longer wavelengths means less of the energy. So that's easy to understand. Somewhat more complicated loss is something called thermalization loss, and this happens when the incoming photon has too much energy. So the energy of the photon is much larger than the band gap, okay, as shown here. So then what happens is that it can get absorbed, but then the electron gets kicked out from, not from the edge of the valence band, but from deeper inside the valence band, and it can get kicked up into, high up into the conduction band, not at the edge of the conduction band. So this is the very large energy. So you can see this arrow is longer than this arrow. So that's the extra energy. Now this is now called a hot electron and a hot hole. And this has too much energy, and something called thermalization happens very quickly. The extra kinetic energy of the electron in the hole very quickly gets transmitted into the crystal structure of the semiconductor in the form of heat, or phonons. Okay, and they relax very quickly to the band edge. So this extra energy is lost as heat, and that's called a thermalization loss. And you can also have something called a radiative recombination loss. What that means is that, let's imagine that this happened. The photon is absorbed, the electron hole pair is created, but instead of this electron going to the terminal, it will simply come back down to the valence band and emit a photon, just like an LED. So if a material can absorb a photon, it can also emit a photon. And this is why, for instance, you will learn later on, a good solar cell is also a good material for an LED, light emitting diode. Okay, so these are competing processes. So instead of forming a current, it just generates another photon. So this is not good. This is treated as a loss. So you can see the three main loss mechanisms: non-absorption loss, thermalization loss, radiative recombination. So non-absorption happens when the photon energy is less than the band gap. Thermalization happens when the photon energy is much larger than the band gap. Radiative recombination happens in all cases, but particularly when the energy is larger than the band gap, because you need to have this carrier generation. Okay, now how do these affect the total efficiency? So if you look at the efficiency going from 0 to 100%, you can see where these losses come into play. So a conventional single junction solar cell, which is like a silicon PN junction solar cell, which is the most common solar cell out there, has an efficiency, theoretical maximum efficiency of something like 24, 25%, something like that, or maybe a little more, 29%, something like that. So that's what this green bar is. So then the question is, what happened to the rest of it? And this is described in some detail in this paper from 2012. But the most important loss, which is the biggest chunk, is this light blue part, which is the energy lost due to thermalization and lack of absorption. So you can see this huge chunk is certainly more than the original efficiency, the theoretical limit as well. So it's a pretty huge, significant impact, right? This is maybe over 40% or so. And there's other smaller factors which we have kind of talked about briefly. There's a loss due to incomplete light trapping, reduced quantum efficiency. There's a loss due to angle restriction, which is kind of related to the light trapping idea. Then there's a loss due to non-reciprocity, which comes from thermodynamics. Let's not worry too much about it. There's a loss in absorption or emission. And then finally, there's a loss due to the Carnot cycle, because you cannot really get 100% because of the heat engine. Again, the second law of thermodynamics. But the most important loss here is this part. And this is the loss that we're going to try to minimize. Okay. So the most common approach to try to minimize this loss is to use what's called a multi-junction solar cell. And all that means is, instead of using a single junction, you use multiple materials on top of each other. So you have a bottom solar cell made of germanium, which has a small band gap. And then you have a middle solar cell made of indium gallium arsenide, which has a middle band gap. And then you have a top solar cell in this example made out of indium gallium phosphide, which has a high band gap. So what happens is that when light comes in, all the high energy photons get absorbed here. Then the photons that do not have enough energy to get absorbed here pass straight through into the bottom next cell. And the next higher energy photons get absorbed here. And even lower energy photons pass straight through. And the lowest energy photons get absorbed here. So this way you can separately absorb the different energy photons in the different materials, and which is illustrated in this spectrum plot. So this gray is the AM1.5 spectrum. The blue is the high energy photons, the short wavelength that gets absorbed in the top cell, okay, indium gallium phosphide. Then the green is the middle energy photons that get absorbed in the middle cell, indium gallium arsenide. And then the pink is the lower energy photons that gets absorbed in the bottom cell of germanium. So by separating this out, you can actually absorb more of the light more efficiently, and you can get a much higher efficiency of the total system. In fact, the world record for a photovoltaic system is roughly was achieved with a cell which looks like this, something like a multi-junction cell, but with high concentration, and the efficiency record is about little more than 40%. So much higher than a traditional silicon cell, which would be about 25%. Okay. However, this is a very expensive proposition for various reasons. First of all, you can imagine you have to grow all these different materials, and these materials have to be grown atomically perfect. So when you grow these crystals, they have this crystalline, nice periodic crystalline structure. If you miss one atom, or if you add an extra atom, for instance, as you're growing from top to bottom, here you added an extra atom, and that causes a defect, and it starts stretching the bonds, as you can see here. And this is very big problem for a solar cell because electrons and holes can get trapped by these defects, and that will drastically affect the performance of the solar cell. So this means that when you grow these types of crystals, you have to grow them in an extremely precise, very, very clean, very, very, very slow process. So this turns out to be very, very, very expensive. So a cell like this can cost about 1,000 times more than a traditional silicon cell, or even more. However, there are situations where this is much more important. The efficiency is much more important than cost. A good example is in space, right? If you want to send a Mars rover to Mars, you don't care about the fact that your solar cell is 1,000 times more expensive, because you need the power. You don't have a choice, and you would rather get efficiency that is 3 or 4 times more. And of course, the reason is simple because, you know, if you have higher efficiency, the weight of your solar cell goes down, and the weight is very important when you're sending something into space. The cost of launching a kilogram into space is much higher than the cost of any of these solar cells. So that would be an example where this is useful. And you have another interesting problem also coming from what's called current matching. And as an electrical engineer, some of you may appreciate this, is that if you look at the solar spectrum, okay, this is the M1.5 spectrum, again, just plotted in a slightly different unit. And if you, let's say you collect this portion of the spectrum, you have a certain number of photons, and that creates a certain number of electrons, which creates a certain amount of current, okay, which is shown here. Now, this portion, and that's produced in the top cell. And this is the middle portion of the spectrum, which produces, let's say, this much current. Now, the bottom cell has a lot more photons because it's much broader, right? You have a lot more photons here. So that means you can create a lot more electrons. So you can create more current, okay? So its current is actually much higher than the top and the middle one. Unfortunately, if you look at this architecture here, the current has to flow through all of them in series. So this is the top one, it creates some current. This is the bottom one, creates some current. This is the, it's the middle one, creates some current. This is the bottom one, creates another current. All of them has to pass through, so it's all connected in series. So if this produces a lot more current than these two, that current doesn't have anywhere to go because it needs to match the current produced by everything else. So this excess current is simply wasted. And another way to think about it is that when you connect these cells in series like this, you are limited to the lowest performing cell in terms of current. Okay, and that's kind of like a architecture level loss. Okay. So overall, this becomes a very expensive proposition. So I want you to think about this problem that we've talked about and see if you can come up with some clever ways of solving this. And Apratim will lead a brainstorming, and let's spend like 2 minutes or so on this. This is a difficult problem, and I want you to kind of discuss among yourselves and think about how you might address it from your knowledge of optics so far. Let me reiterate the problem. The problem really can be thought of like this. Your solar spectrum is very broad. So how you cannot absorb all of these photons with a single material efficiently. So people try to stack multiple materials next to top of each other to absorb them efficiently. But when you stack them, there's this expense part, and also you have the current limitation part because everything is connected in series. So let's spend a minute or two to see if you can come up with some clever ways using optics or otherwise to solve this problem. So feel free to talk to your neighbors. And you can tell Apratim